Hello everyone, welcome to the video on Visualizing CNN by Society of Artificial Intelligence or SOAI. I am Ritul and this PPT is created by my colleague Tushar. Let's start. Visualizing CNN, receptive field of a neuron. What does a filter learn? What kind of images cause certain neurons to fire? How good are the hidden representations? To answer these questions, we need to talk about the receptive field. Consider a three-layered CNN, where in each of the layers we apply a 3 and 3 filter. The receptive field or region of influence of the neuron or pixel in a subsequent layer refers to all the neurons and pixels from the previous that were involved in the convolution operation to produce said output neuron or pixel. Let's look at layer 3 and express the receptive field in terms of layer 1. Thus, we can see that the 3 and 3 grid in the receptive field of the layer 3 pixel translates to a 5 and 5 grid receptive field in the input image. We can see a sort of pattern whereby if we have more layers, the receptive field becomes larger and larger in the input image. If there was another layer 4 with the same 3 and 3 filter, it would correspond to a 7 and 7 receptive field in the input layer. The following diagram illustrates how the receptive field in the input layer is larger and larger as we move down the layers. The increase in receptive field size through the layers increases with a larger filter size. Identifying images which cause certain neurons to fire. From the previous section, why is the concept of an increasing receptive field important? Consider the same diagram from the before. Now, what does firing mean? In the case of sigmoid neurons, it refers to when the output approaches 1. In the case of real U and leaky real U, it refers to any large positive value greater than some threshold. Here are the results of an experiment to understand the firing of different neurons. Consider the following layers with our 256 and 23 and 23 neurons. Some neurons are sensitive to, let's say, images of cats, while others are sensitive to images of aeroplanes, etc. Now, we need to see whether different neurons fire to different inputs and what are these which cause the neurons to fire. In the above image, the firing of 6 different neurons was observed across the training set of 1000 images. Each neuron is shown to be sensitive to particular inputs as shown in the figure above. This analysis helps us to understand whether neurons in different layers are learning some meaningful patterns and having some discriminatory power instead of all of them firing for all types of input. Visualizing CNN, visualizing filters. We have dealt with filters in all our CNN so far. Now the question is, what exactly does a filter capture? Let's look at the working of a 2 and 2 filter on a 4 and 4 input image. Here, the input image is 4 and 4 while the filter is 2 and 2. The red input pixel vector x is x1, x2, x3 and x4. The weight vector w. By convolving the input pixels with the filter, we get output. Output at 14 is equal to w1 x1 plus w2 x2 plus w3 x3 plus w4 x4. H14 is w multiplied with x. This is the same as the dot product between the two vectors. H14 is directly proportional to the cos of theta, where theta is the angle between the two vectors. Now, for certain inputs, we want the filter to fire, give a high value. Now, H14 will be high when cos of theta is high. Cos of theta here is equal to 1, that is, when theta is 0. This implies the two vectors w and x are in the same direction. So, we can say that an input vector which aligns with the filter yield maximum output. The neuron H14 will fire maximally when x is equal to w divided by mode of W. X is an input vector in the direction of W. Thus, when we slide the 2 and 2 filter W across the 4 and 4 input region, whenever we reach a 2 and 2 region X that looks exactly like the filter, we get a high output. For all other regions which do not align with the filter, the output is low. The above image shows us how different patterns are identified by different filters. We can determine the maximally contributing regions in an image using occlusion experiments. Occlusion experiments refer to applying occlusions to the input image and seeing how they alter the predicted output distribution. Then we take the difference between the unoccluded distribution and occluded distributions for occlusions placed in all patches of the images. These differences allow us to generate a heat map of maximally contributing patches. Consider the following images with occlusions applied to them. Occlusion experiments. The true distribution for any of these images would be say y. The unoccluded predicted distribution y1 cap is equal to 0.89. Occlusion placed at position y2 cap is 0.84 and occlusion placed at position L y n cap is equal to 0.3. Now calculating the difference between y1 cap and summation from n equal to 2 to I of y n cap, we get difference in probabilities, which can be plotted as a heat map over the input image with colder regions being more highly contributing. Thus, the higher the difference between unoccluded and occluded distributions, the more significant the distribution of that particular occluded region to the output. Society of Artificial Intelligence, thank you. So it's the implementation part of CNN visualization. So let's look at the outline first. Using torchvision.datasets with a custom folder of images, occlusion analysis with pre-trained model, filter visualization with pre-trained model. Now import warnings. Warnings.filter warnings ignore. Let's import. Also, import some other files such as numpy, matplotlib.pyplot, cboard, torch, and torchvision, etc. So, load dataset. Let's unzip this file. Now, now open this file, print classes. After printing, we get all the classes here. Here, transforms.resize function with values 224, transforms.toTensor function, and transforms.normalize function with values here. Now, evalset is equal to torchvision.datasets.image folder function. Here, root is equal to, you can see, and transform is equal to transform. Batch underscore size is 1. Eval loader is equal to torch.utils.data.dataloader function with eval set, comma batch underscore size, comma shuffle, which is here true. Now data iter is equal to iter function eval loader images comma labels is equal to data iter dot next function. Now print images dot shape. Here is the value of these functions. Now data pre-trained model. After downloading all the necessary files, now model.eval function, it will return this. Now visualize images function imshow function with img comma title as parameters. std underscore correction is equal to np dot sarray function. You can see the values here. Dot reshape function with 3 comma 1 comma 1. Similarly for mean underscore correction and npimg, which is equal to np dot multiply function with img dot numpy function comma std underscore correction plus mean underscore correction. This function will print a image whenever this function will call. Similarly for show underscore batch underscore images function with parameter as data loader. Now images comma print is equal to show underscore batch underscore images function. Here we pass a value here which is eval loader. So this function will call this function and we get this clipping input data to the valid range from IMSO into RGB data. You can see here. Now occlusion analysis. Outputs is equal to model function. Here images is a parameter. Now print output dot shape. This is the value for output dot shape. Now outputs is equal to nn dot functional dot softmax function with outputs comma dimension with dim is equal to 1. And finally this will print probe underscore no underscore o. The value is here. Now occlusion function with model comma image comma label comma oak underscore size equal to 50 comma oak underscore stride is 50 comma oak underscore pixel is 0.5. These values are as parameters. Now width height is equal to image.shape comma image.shape of -1 output underscore height and output underscore width. Heat map is equal to torch.zeros function and so on. This function will finally return heat map. Now heat map is equal to occlusion function here with parameters here and img plot is equal to sns dot heat map function. Here are the parameters which we are going to pass as this will print this image. Now filter visualization. So download the necessary file and print lxnet. After printing we get the values. Now plot underscore filters underscore signal underscore channel underscore big function with parameter t and next function which is plot underscore filters underscore signal underscore channel function with parameter st. This will plot the image. Similarly plot underscore filters underscore multi underscore channel function with parameter st. This will print the images as you can see on the screen. Plot underscore weights function lxnet comma 3 comma signal underscore channel is equal to true. After calling this function we get this image as an output. Similarly for plot underscore weights function. Similarly for all. Society of Artificial Intelligence. Thank you again.